Hey everyone and welcome back to PrepFusion. So today we'll start the first lecture 1 of power electronics. This is the semiconductor devices or switches, right? This is the first chapter. So in the previous chapter we learned about different type of switches. Why do we need power electronics? Also we did few numericals on switching losses and conduction losses. Like the last question was very good. I hope you have solved that question. So now we'll start with our power electronic switches. We'll basically get the specifications of each of the switches and what type of switches do we use, and we'll learn few terms related to power electronic switches which are commonly used for classifying the switches. Also we'll study completely power diode in this lecture, okay, and in the next lecture we'll study about different transistors, power transistor. So here there are a few basic terms that you should get an idea, and don't worry, as we go along you will know about all of these terms undoubtedly. So the first term is unipolar. What does unipolar mean? Unipolar mean can only block voltage in single direction. Sometimes unipolar can also be mentioned as in this type of devices, right? Unipolar devices, there is only a single charge carrier, okay? Only one type of charge carrier is present in unipolar devices, not two. If you don't understand about charge carrier, if you don't understand about majority minority charge carrier, obviously I have given the prerequisites. You have to go and watch the prerequisites. There all the things have been explained. Charge carriers, what do you mean by majority charge carriers, what do you mean by minority charge carriers. Obviously I will also explain here, but not to that much of depth because I don't want to waste your time. You have to go to the prerequisites, okay. Also bipolar means it can block voltage in both directions, both positive and negative. It can block both voltages in both directions, right? Sorry, it can block voltages in both direction. Now bipolar also can be can also be said like in a bipolar device there are two charge carriers, both electrons and holes. In a unipolar device only one charge carrier is present, only electron or only holes, not two, not both. In bipolar both electron and holes can be charge carriers. Now what about uncontrolled switch? Uncontrolled switch or passive switch means on/off cannot be controlled by an external signal. We cannot externally control on and off signal. It will depend on the input signal only. Whatever input I am giving to the switch, by input I mean whatever the supply is. I can't control the supply, right? But I can control. I should be able to control the on and off of the switch, but I am not able to. The on and off of the switch is just a function of the supply voltage, and I cannot control the supply. So hence, I cannot control the switch. Okay, I cannot control the on and off process. A semi-controlled or a half-controlled switch, which is also known as active switch, it can be turned on or off by a external signal, but not both. So let's take an example. SCR, right? SCR, if you know about SCR, very good. If you don't know, we'll study about that. So in SCR we can turn on the SCR with the help of an external signal known as gate triggering, but we cannot turn it off. With the help of external signal we cannot turn it off. We can only turn on the device, we cannot turn off. So it is a semi-controlled switch. So these type of switches are known as semi-controlled switch. Now fully controlled switch. Fully controlled switch means, or active switch, it can be turned on and off by an external signal. Both are possible. So we'll study about these type of switches also, which is fully controlled. I can fully, name suggests itself that I can fully control the switch. I can control the turn on process and I can control the turn off process as well, okay, with an external switch, not with the input voltage. Okay, I don't care about the input voltage. I can on my own give a external signal to the switch that turn off now. I can give a external signal to the switch to turn on now. Okay, so and firing circuits are basically those circuits which provide the external signal to the semiconductor switch to turn on and off. Okay, we'll study about this in SCR, don't worry. So these are the few terminologies that you should have a basic idea of. Now what are different power switches? So diodes, today we'll start study about power diodes. On and off states are controlled by power circuit. So basically this is uncontrolled, right? This is uncontrolled switch. So power diodes fall in the category of uncontrolled. Now thyristor is basically a family of few semiconductor devices which we'll study later on, and these are latched on by a control signal but must be turned off by power circuit. So these are semi-controlled. Because this can be turned on but we cannot turn off with the help of an external signal. We can only turn on with the help of an external signal. Semi-controlled. I cannot Just hold on. Control. What about controllable switches? This can be turned on and off by control signals. So like this same thing they have explained here only. The like controls. What are the different categories of controllable switches? Basically, it is a transistor family and also thyristor also present. So basically, BJTs, MOSFET, gate turn off thyristor, and insulated gate bipolar transistor. They are having major category in this category of devices, major advances in this category of devices. Basically, these are the fully controllable switches. So I've given you example of semi-controlled, uncontrolled, and fully controllable switches. Okay, so let's study about few more commonly asked terms. One is the majority charge carrier. So what do you mean by majority charge carrier? Here, right, only one type of charge carrier is present, either holes or electrons participates in conduction. So when the conduction happens in the device, right, when the conduction happens, when current flows in the device, only one type of charge carrier is responsible for the current flow, either hole or electron. Yeah, hole or electron, right, not both. For this to occur, there must be no PN junction in the path of the current flow. Okay, so in a majority charge carrier device, there must be no junction, PN junction, in the path of the current flow, as only one polarity of charge carriers are present. Hence it is also called a unipolar device, as I have mentioned previously as well. Minority, what do you mean by minority? Minority means both holes and electrons contribute to conduction. So from where do we get this majority and minority name? Majority means majority of the portion, majority of the current is flowing due to particular one charge carrier. That's why this is known as majority charge carriers. Minority means like bit of current is flowing due to electrons, bit of current is flowing due to holes. So both electrons and holes are minority here. Here one charge carrier will be majority here. So that's why this is minority and this is majority. So both holes and electrons contribute to conduction. When holes move from the p channel to n channel, they become minority carriers after moving from the n channel to p channel. So like this happens because there is a pn junction, and like they become minority charge carriers in the other junction, in the other layer. In this layer they are fine, but in the other channel they become minority. In their layer they are majority, but in the other layer they become minority. So if you're not understanding, please you have to go to the prerequisites and watch the semiconductor physics and all those things. Whatever I've said, you have to watch those prerequisites. So that is the thing. Therefore it is a minority charge carrier device. There is a PN junction in the path of the current flow. So in case of a minority charge carrier device, there will be a PN junction in the direction of the current flow. Conduction happens due to both polarity of charges, hence it is called a bipolar device. So bipolar device, I have already told you that due to both polarity of charges, if the conduction is happening, so it is called a bipolar. So the same thing has been explained over here. Now let's understand few more things about minority charge carrier devices. So minority charge carrier devices have depletion layer due to formation of PN junction. So in a PN junction, depletion layer is formed when it is forward bias. These junctions have mainly two operating regions, forward bias and reverse bias. Forward bias and reverse bias. During forward bias, charge carriers get injected. So all this working, right, it has been explained in the working of diode, so I'm not going too much into this. So I hope you watch the video. During forward bias, charge carriers get injected into injected in the junction. Hence what happens is the depletion width, the width of the depletion region reduces, right? Depletion layer, width of the depletion layer reduces. During reverse bias, charge carriers get depleted. The charge carriers are lower as it is reverse bias, hence depletion width of the PN junction increases. The depletion width increases, hence the flow of electrons or the flow of current becomes more and more tougher. The time taken for this injection and depletion of charge carriers are known as on time and off time. So basically when the diode is forward bias, it is on, right, and when it is reverse bias, it is off. Basically why? Because when the diode is reverse bias, no current flows, and when the diode is forward bias, it can flow any current. Obviously we have to flow current within the limits that I am within. Okay, that I am assuming that I am within the limits. Then obviously if the diode is forward bias, it is on, and if the diode is reverse bias, it is off. So what it is telling that for it to be on, right, charge carriers need to move, and what happens? Reduce the depletion width. Okay, and like charge carriers are injected in the region N region and the P region, and then what happens? The depletion width reduces. All of this, right, this is a continuous process. Obviously this takes some time, and that is exactly what it is telling here. I told you, right, previously, switching on and switching off, it was increasing linearly, this was decreasing linearly. Current and voltage were increasing and decreasing linearly. So here what is happening here, this charge carriers, right, this charge carrier are getting injected or depleted from the p and n layer, and that is taking some time. That will take some amount of time for electrons to move. So that's why there will be some on time for a switch and there will be some off time. In the case of diode as well, there will be some on time for the diode to be completely conducting, or there will be some off time to completely be insulated, and it should pass zero current. So this is the on and on time. Hence the maximum switching frequency is given as this 1 by T on plus T off. Now basically what is happening, due to this T on and T off, maximum switching frequency is reducing. I've told this previously also as well. This is a practical switch, right? So how do you compute the maximum switching time? I am not giving it any time. I am not giving the switch any time. As soon as it turns on, I am turning it off. Then as soon as it turns off, I am turning it on again. Okay, so to turn on, it took T on time. I gave it T on time. Then as soon as it to completely turn on, I turned it off again. So again it will take T off time to completely turn off. So obviously the frequency of this, okay, lowest possible time between each on and off is, like in this case, f switch max can be 1 by T on plus T off. Basically capital T on, capital T off will be 0, right? The time period for which it is completely on and the time period for which it is completely off is 0 in this case. So that is basically what this means. 1 by T on plus T off is the maximum switching frequency. Basically here I will explain. It is instant off and on. Okay, so basically what is happening is our FSW, right? FSW is reducing. If you remember, our switching loss is reducing. Okay, why is it reducing? Because our T on plus T off is increasing, right? T on plus T off is increasing. Now if you remember correctly, that our what to say, P, like switching loss, right? Switching loss was equals to proportional to T on plus T off, right? If you remember, it was proportional to T on plus T off. If you remember, in the previous lecture we derived all this. So as T on plus T off is what is happening, it is increasing. T on plus T off is increasing. This switching loss will also increase, right? It is directly proportional. So T on, the amount of time it takes to turn on, the amount of time it takes to turn off, the device is taking in energy from the input and not giving it to the output. Instead it is using it for its own purpose to turn on, right? And we don't want that. Obviously we want all the energy to go to the output, not to the power circuitry, not to the control system. Okay, obviously it is not possible. Ideally, practically it is not possible. We want to minimize it as much as possible. But in this case, what we are observing is my T on and T off are increasing, the power loss increases in the switch. That is inevitable. Now another few points about minority charge carriers is that minority carrier devices have conduction modulation, hence on resistance and conductivity loss are much lower. What do we mean by conduction modulation? We'll understand, don't worry. When we will study about power diodes, there I will explain about conduction modulation. Now BJTs have negative temperature coefficient, hence BJTs are not suitable for parallel operation. So like what do we mean by negative temperature coefficient? Like there is a problem known as secondary breakdown problem or thermal runaway in BJT, if you have studied analog electronics. So here what happens is that the temperature increases, hence the resistance decreases for the BJT when it is on, and if the resistance decreases, what happens is that the current increases. Just hold on. The current increase. Why? Because BJT is connected in series or parallel. If it is connected in series, what will happen? The resistance decreases, hence the drop decreases, hence the current, more current will flow, because the overall, like I equals to V by R reduces, so I increases, right? Now if I increases, again if current increases, the temperature will also increase, right, inside the device. The more the current, the more the hotter it gets, and this loop goes on, and that is a huge problem that we will see this when we analyze BJT. And that's why I have given this point here, because BJT is also a minority charge carrier device, and this point is important to note over here. Like we will understand, we will go more about this in the BJT lecture. Now like here are the main key points, and you should put this in your short notes, okay, if you want to remember all this in a single slide. So in a single slide, basically majority charge carrier devices have only one type of charge carrier, no PN junction, and like they have both holes and electrons as charge carrier. The minority one, PN junction, they have PN junction. These have low T on and T off. Why these have low T on and T off? Because they don't have any PN junction. If they don't have any PN junction, the from the depletion, the time taken for the depletion width to get smaller, the width to get smaller or the larger, right? It doesn't take any time for this majority charge carrier devices. Okay, but it does take time. So it is high T on and T off. This is low T on. Hence, these type majority charge carrier devices will have high switching frequency. Minority will have low switching frequency. This will have lower power loss, switching power loss. This will have more power switching loss because more of the time is going in the switching itself. Then this has higher turn on resistance. Why? Because this doesn't have conduction modulation. We will study this has conduction modulation. That's why this has lower on resistance. So we'll write here conduction modulation. Conduction modulation. Okay, and like we understand this later on, don't worry. And the examples are power diode, SCR, BJT, IGBT, track, GTO, and here the examples are simple Schottky diode. Okay, we'll understand about this as like just the points, key points, and MOSFET and other devices as well. So these are the examples. These are the main crux of majority and minority charge carrier devices. Now we'll study about the power diode. What is a power diode? A power diode is just like a normal diode, but there are few differences in the construction of a power diode. So like I have told you to study the diode, normal diode, the construction of diode and the working of diode, right? And the power diode will always be same, but few things will be different, we'll understand. But the symbol of a power diode will be same as the normal diode. Powered semiconductor diodes are similar to low power PN junction diode, which we studied in analog circuits, known as signal diodes. So those diodes which we studied in analog circuits are also known as signal diodes. However, powered semiconductor devices are more complex in both structure and operation than their low power counterparts. So the structure and operation of a power diode is a bit different and more complex. We'll understand that slowly. This complexity arises because low power devices must be modified to be suitable for high power applications. So in analog electronics, we mainly work with 5 volts, 10 volts, or 20 volts, or at max, let's say 50 volts. But in power electronic devices, this switch is working in 230 volts. So obviously, this charger, this charger go. So this charger has to work in 230 volts. So obviously, we have to support high power structures and all those things, so that it can it can absorb that much amount of power, it can resist that much amount of power. It must have that construction, that rigid construction. So obviously, to do all this, we have to modify our normal signal diode, because those were made for low power application, low voltage applications, not for high power applications. So we have to make few modifications. We'll understand that. So basically, what modifications we make? For instance, power diodes are constructed with an N layer called drift region. So this there is a different N layer. So in normal diode, there is a P layer and N layer, right? But in power diode, there are 2 N layers. One is lightly doped, one is highly doped, and it is talking about this lightly doped N layer. This is called the drift region. The lightly doped N layer is called the drift region between P layer and the N plus region. Okay, cathode. Between the anode and the cathode, there is a separate N layer, which is N minus, right? This is the N minus layer. Okay, I will not do this because they will get confused. So in the diagram, it is shown. Obviously, we'll go through this. Let's first study this. Read this. This modification supports large blocking voltages. So due to this N minus, right? So the depletion width now will increase, right? The width will increase. Hence, it can support higher voltages, higher reverse voltages. It can block more higher amount of voltages. So obviously, that's why we put this N minus layer. And this N minus, right? This N minus is also called the drift region. You have to understand this. Whenever there is a N minus or lightly doped region, we modify it. That region is known as drift region. The N type layer is not present in signal diode. So this drift region is not present in signal diodes. Just P and N are present. Okay, but this drift region is not present. But power diode has some modification. So in signal diode, if we just change our N region into N minus and N plus, that will become a power diode. That is the modification. And obviously there are more complexities, but we are not going into that. The main change that we do is this one. Okay, so here now, right, there are three regions now. This this is one junction, this is also another junction, but here not much of a junction forms because n minus and n plus, not much of a difference, right? But here, right, as this n minus, this is highly doped, and this is or moderately doped, this is, and this is lightly doped, and this is highly doped. So this, right, with this what happens is that the junction width will increase. This region is known as the drift region. Previously there was only p plus and n plus. Now there is this n plus due to this. Now there is this n minus, due to which the width increases, the junction width increases. Hence, this region is known as the drift region. Okay, and due to this, it can support higher reverse voltages, because what will happen is that this will be highly depleted of charges. Hence, the width will be more. And as the width is more, it can support higher reverse voltages. That is the reason, to support higher reverse voltages. So we can see, right, the width W2 will be like this. W2 will be largest, then W1, then W3. This will be very small, right? Like this is present just for the conduction support during the forward bias. During the reverse bias, it must block higher voltages. This is there for the reverse bias. This is there for the forward bias. We'll understand the working slowly. There we'll understand this. Don't worry. Okay, so this is the construction, and this is the basically definitions of all those things. And let's first read few points. The voltage blocking capacity of any semiconductor device is proportional to the width and doping of the layer. So doping of the layers and the width. So this is very lightly doped, and the width is very large. So the charge carriers have to travel very long path, and this is also very low amount of charge carriers. That's why the resistance will be more. Hence, it has more higher blocking power blocking capacity, and hence very less amount of current will flow. And exactly that is what is telling it. Voltage blocking capacity of any semiconductor device is directly proportional to the width and doping of the layer. To pass high current in conduction mode of a semiconductor device, we require large area to provide fast conductivity. We must have one highly doped N layer in the semiconductor device. So this is explaining the design of this power diode, why we had this N plus. This N plus is there, as I explained previously, for the conduction mode. When the diode is in forward bias, it needs to flow high amount of current, right? And it needs higher area. So this layer is thin, but the area is more, and this is highly doped. So we need charge carriers, right? And this will provide those charges. This will provide those charge carriers when high current is flowing in the forward region or in the conduction mode. In the reverse region, this is helping to block the voltage, and this is helping the forward region to pass the high current. Okay. So this is the thing basically. Basically what mainly it does is it keeps the current density constant as there is more higher amount of charges, and as the area is larger, right? As the area is larger, it keeps the current density constant. We have to keep the current density constant. If the current density is very high, this will burn the device. I hope you know, right? If the concentration of current is very high in a particular region, that will just be too much for that particular device. That will burn the device. So we have to anyhow make the current density constant. That is our aim. That's why we have a highly doped region, and that region will have higher area, even though it is like width is lower, but area is high. Width is for voltage blocking capacity, area is for current passing capacity. So these two things you should keep in mind. So this is to keep current density constant. Okay, to keep current density constant. Now let's understand the construction. Power devices are constructed with vertical orientation, as this structure allows for greater cross-sectional area. So we design power devices in vertical fashion. This may be come in MCQ or ESC or someplace, right? Just hold on. Let me check if everything is fine and recording. Yeah, everything is recording. So this might come in ESC or something. Gate doesn't give this type of questions. So why do we construct in vertical orientation? To have higher cross-sectional area. Higher the cross-sectional area, higher the current carrying capacity. Okay, the cross-sectional area of a power diode is determined according to its current rating. Highly doped P plus region and N plus regions contain more charges, enabling a higher current rating. If the doping in the P and N region is reduced, the current rating of the device obviously will reduce, as explained previously as well. Now, what are the properties of a power diode? Just same as normal diode. Okay, the symbol is same, everything is same, just it supports higher reverse voltage blocking capacity. Okay, the avalanche breakdowns occurs much later. That is the thing. So it is a two terminal device, and the terminals are named as anode and cathode. It is a 3-layered uncontrolled unipolar unilateral passive device. Why is it called uncontrolled? Because I cannot control the turning on and off. Only just the voltage across the diode will, like the input to the diode will control the on and off, right? If the voltage is more than the forward voltage, then it will be forward bias. If the voltage is if the anode to cathode voltage is negative, then it will be reverse bias. No current will flow. I cannot control it. Okay, it totally depends on the anode to cathode voltage, which is determined by the input. Why is it called unipolar? Unipolar because it can only block reverse voltage. It cannot block forward voltage. Right? If the anode to cathode voltage is positive, it will turn on. Nothing can control it. Okay, it has no voltage blocking capability. That's why this is called unipolar. Unilateral because current can only flow in this direction. Current cannot flow in this direction. Okay, like obviously some reverse saturation current will flow, that we ignore. Then this is a passive device because this has no supply in it. That's why this is a passive device. It is a minority charge carrier device. Just do keep this in mind. Yeah, sometimes minority charge carrier device can also be unipolar, even though here both holes and electrons are supporting for flow of current, but this is still a minority, like that's fine, right? Both holes and electrons are supporting, that's why this is a minority charge carrier device, but this is unipolar. So sometimes confusion has been occurred between this unipolar and bipolar thing. What does unipolar mean? Mainly unipolar means about voltage blocking capability, whether it can block voltage from both sides or single side. But sometimes unipolar also means what type of charges are flowing, whether both polarities of charges are flowing or single polarity. So like there is a confusion, but your first priority should be about the voltage blocking capability, then second priority should be about the charge flow, because in SSC JE and all the lower tier examinations they sometimes ask this unipolar and bipolar, and there sometimes confusion happen, you know, right? There are many questions in ESE as well, like they just frame the question and the question is wrong, you know, some theoretical part is wrong, they just follow their convention, and according to that convention the answer will be that answer will be something else, and according to our convention answer will be something else. So these type of convention also gets followed. Sometimes gate won't give you this type of question that tell me whether this device is unipolar or not, but in ESE, SSC, JE, all those examinations sometimes this confusion may arise. Okay, so I have cleared that confusion now. Now safe operating region is in the second quadrant, or you can say not in the second quadrant. For an ideal, right, ideal power diode, basically there is like the operating region is just in this, right? Either the current can be positive or the voltage can be negative. Okay, and the current is 0 in this. So basically this is the safe operating region in which my diode can operate for an ideal diode. But for a practical one, basically we know the practical one, right? How does a practical diode characteristics happen? So here I have drawn two. One is the signal diode and one is the power diode. So what is the difference? In the figure itself you can understand what is the difference, right? Basically in the signal diode the reverse voltage breakdown occurs much earlier than the power diode because it has higher voltage blocking capability, and the voltage drop, forward voltage drop, is also much lower for the signal diode and the power diode. Obviously it has n minus layer, so we will need more voltage to turn it on, to forward bias it. Okay, and this is happening due to the drift layer basically. Okay, so like I have drawn these two to compare, and I am not explaining these characteristics because this has been already explained in the diode prerequisite chapter. That's why I am not wasting any time here. Okay, so I hope you watched that. Drift layer is used to increase reverse breakdown voltage. So I have already explained this previously also. Signal diode has exponential VI characteristics. This I think has been proved in the prerequisites. Drift diode has less doping, less number of charges, higher resistance. Hence voltage drop across it becomes I into R. So what happens is, as it has higher resistance, right, and it has less doping, so this, right, this voltage drop across the drift region almost becomes linear. Why is that this is the case? Because this, right, VD upon eta VT, this almost becomes linear. That's why. So we can linearize our power diode. Generally this doesn't happen, but we can linearize, right? So we assume that this R resistance is almost constant, so the drop across the power diode will be linear. Okay, it will be linear. As current increases, this will also increase linearly. So what happens is, generally in case of power diode we assume this is a assumption that we do just to simplify our calculations. We linearize things. Okay, so this drop dominates exponential characteristics, hence forward bias curve appears to be linear. Okay, as in the forward bias, like this was supposed to be exponential, but we assume that this is linear. Okay, and this linear portion dominates the exponential portion, that's why we assume it to be linear only. There will be some error, but that's fine. How does drift layer increase the reverse breakdown voltage? So for this, right, you need a bit of knowledge of EDC. Whatever I am going to write, if you have knowledge of EDC, you can obviously understand. If you don't have, ignore this part. So in drift layer, right, what is happening? The number of in this layer, this is the P region and N region, and I have told that P region is moderately doped and N region is lightly doped. Okay, so what is happening? The number of acceptor ions here, I will write here, Na is moderate, just hold on, moderate, and number of donor ions is very low. And if you remember the formula of V breakdown in a PN junction diode, if you have studied EDC, you will know. If you don't have studied EDC, don't worry about this. So VBR, the formula is something like this, is equals to, it is inversely proportional to Na plus Nd, right? It is somewhat like this, inversely proportional to 1 by Na plus 1 by Nd. Okay, other things are there, I don't care about those things. So here what is happening is that my Nd is getting lower. So if my Nd is getting lower, what will happen? Overall, this is moderate, Na is moderate, just hold on, Na is moderate, but Nd is getting lower. So overall this VBR will obviously increase. It will not get lower, it will only increase, right? So this is the important thing about VBR. So like that's a basic proof that I wanted to give for the people who want to understand in formula how does this VBR increases breakdown voltage. This breakdown voltage increases, but intuitively you can understand, right? Number of charge carriers are lower, the length is more, width is more, right? So the charge carriers get more resistance to flow. They have more resistance, right? I have to walk 1 kilometer. Instead, I have to walk 5 kilometers. So that is more tougher, right? So it is more tougher for the charge carriers. That's why the breakdown voltage is also more higher. Once the charge carrier flows, obviously everything will get breakdown, and avalanche breakdown will occur, and the device will get damaged. That we know, that we have studied in diode characteristics. Okay, so that is what I wanted to explain over here. So let's now go to another part, that is the conductivity modulation. So what is conductivity modulation? So this is during the forward bias. During the forward bias, holes from the P region holes from the P region to N plus holes enter from P region to N plus, and electrons from N plus to N minus. So if I just copy this diode, right, if I just copy the structure of this diode, here what is happening is that, like, P has what? Abundant amount of holes. It has Na acceptor ions, holes, right? It has holes. P has holes, and N plus has what? Electrons. N plus has electrons. And as it is forward bias, that means I'm giving positive to anode and negative to cathode. VAK is positive. As it is forward bias, what is happening? The holes will get what do you say about that? Repelled. Holes will get repelled from this positive, right? They are of same sizes. Hole has positive charge. This has also positive charge, so they will get repelled. So holes will get repelled, so they will try to flow in this direction, and electrons, right? Again, this is negative and this is also negative, right? So they won't get attracted. They will get repelled. Again, holes will electrons will flow in this direction, right? So this is telling the exactly same thing. So holes enter from the P region to N plus region. Basically N plus means here they will enter here only, okay, because they can easily pass through this, because this is forward bias. Now there is no depletion, the depletion width will be very low in the drift region, and electrons from the N plus region will flow to N minus region, and like it will, sorry, this will be N minus, this will not be N plus, this will be N minus, right? N minus, yeah. Basically holes are coming from this to N minus, and electrons also coming from this to N minus. Charge concentration increases in the drift layer. So in this layer, right, obviously the charge concentration will increase. Holes are also flowing, electrons are also flowing, charge concentration is increasing. Now as the charge concentration is increasing, obviously conductivity increases. So the number of the conductivity is directly proportional to the number of charges present. So this phenomenon is basically called as conductivity modulation, nothing else, right? So when this is positive forward bias, so holes are going into this n minus region and electrons also are going into this n minus region. So the amount of charges present in this drift region is increasing, and as this is increasing, the width also reduces. And what happens is that number of charge carriers increases. If the number of charge carriers increases, the conductivity increases. Hence, what will happen is that it will flow more amount of current, and this is known as the conductivity modulation, the increase of conductivity. And as conductivity increases, the drift resistance will decrease. As conductivity increases, the resistance offered at the drift region decreases. Hence, conduction losses reduces. Conductivity increases, it supports more conduction, so resistance will reduce. Hence, the conduction loss when the diode is on will reduce. Obviously, we know it is proportional to the on resistance. We have computed the switching losses, right, or the conduction losses as well. So we know that it is proportional to the on resistance. If the on resistance reduces, obviously the conduction loss also will reduce. So here I can say R drift reduces. Okay, R drift reduces. Now, like, there are a few comparisons with normal signal diode and power diode. So power diode has more breakdown, I've already explained. Power diode has more knee voltage, that also you can see from the VI characteristics, and like it is almost equals to 1 volt, and compared to normal signal diode it is 0.7 volts. Okay, power diode has linear characteristics in the forward region and not exponential. Because we approximate it is almost equals to linear, because we're talking about this larger currents and larger voltages. That's why we can linearize it. Okay, so we assume that. So this is basically the IV characteristics of power diode. There are a few regions. This is known as the reverse blocking region, this is known as the forward conduction region, and this is the transient switching, right? So in this region, right, we are just increasing the voltage and just more than the forward voltage. Okay, if you increase the input voltage to more than VF, this will be forward biased. Okay, and this will go into forward conduction region. Okay, so these are basically different regions. So here, right, just if I apply more voltage than breakdown voltage, obviously what will happen? Breakdown will happen, avalanche breakdown will happen, diode will get simply damaged. So this is pretty simple to understand. All this we have studied, and this amount of current, right, this amount of current is the also known as the reverse saturation current, or also known as the leakage current. So all these things we have studied from diode itself, from the prerequisite itself, right? Now, what is the IV characteristics of a practical diode? Like, the IV characteristics of a practical diode should lie in which quadrant? So the safe operating region or area I have told you for an ideal diode, but what about the IV characteristics of a practical diode? In which quadrant should it lie? I have just shown you the IV characteristics, right? It should lie in the what? First and the third quadrant. First and the third quadrant. So this is the first quadrant, right? This is the first quadrant, and in the second quadrant there is nothing present, right? In this quadrant there is nothing present, but in the third quadrant it is lying. Okay, so in the fourth quadrant also there is nothing. So it should lie in the first and the third quadrant, the IV characteristics of a practical diode. So these type of question can come. Now, to adapt a signal diode for high current and high voltage applications with minimal loss, what should we do? What should you do? I've taught you, right? I've taught you just in this lecture itself. A lightly doped N layer is added between two P and N layers. A heavily doped N layer is added between two P and N layers. A lightly doped P layer is added between two P and N layers. A heavily doped P layer is added between P and N layers. So you might get confused between this. Like, obviously we know heavily doped is not possible. We will only add lightly doped to support high voltage, and obviously what we'll do, we'll make the N layer more highly doped. They haven't mentioned it, but they should have mentioned it. Okay, so basically only this and this is possible. Now, why will we choose this and not this? So we have studied about this, right? We will add a lightly doped N layer. Why will you not choose this? So here, basically I have forgotten to mention in the starting of it. I should have mentioned that why we choose N minus and not N plus. We choose N minus, we choose N because electrons have higher mobility, so it helps in conductivity. During conduction it helps, right? That's why we don't choose P, we choose N, because electrons have higher mobility than holes. So we'll write here, we'll write just here itself that, just hold on. what is it? Basically, we choose n minus and not p minus as electrons have, because in n minus, right, electrons are the majority carriers, electrons have higher mobility. Oh no, electrons have higher mobility. Just hold on. What I will do is I will put this at the top. Than holes. So electrons have higher mobility than holes, right? So that is the reason we choose n minus and not p minus. So obviously here option A will be correct and not option C. So I hope you got the reason. Okay. So let's study few DC diode parameters. This you already know. Basically the forward voltage. It is the voltage drop of a diode across another cathode at a defined current levels when it is forward biased. So you have to apply this voltage, then only the diode can turn on, then only current can flow. Okay, else no current will flow. So this is some drop that happens across the diode. We already know this. Now background voltage. Background voltage is the voltage drop of a diode at a defined current level when it is beyond reverse bias level. This is known as avalanche. This background is known as avalanche. Basically just after this VVR, right? If you apply more than this VVR in the reverse direction, then what will happen? The diode will be breakdown. The breakdown will occur across the diode and diode will get damaged. So this is the limit at which we can apply. This is known as the breakdown voltage. Reverse current. Basically IR is the current at a particular voltage, and when voltage is below the breakdown voltage, it is the reverse current. So okay, below means here, right? Below means here. Okay, so it should be below this breakdown voltage. So some reverse saturation current flows through the diode, that is known as the leakage current also. This current is also known as the leakage current. Even though we know the diode will be off when there is some reverse voltage applied, but very small amount of current flows, that is also known as the reverse current or the leakage current. So these are all theoretical things. You should know. I'm just creating all the base so that we can study about the main things, right? Main things. So now let's come to AC diode parameters. So these DC diode parameters you already knew, I hope, but this AC ones I hope you didn't have the information. What is this? Just hold on. Let me check this recording. Yeah. So this AC one is the forward recovery time. TFR is the time required for the diode voltage to drop to a particular voltage after the forward current starts to flow. So what does it mean? So a device requires a finite time to transition from off state to on state. I've already mentioned this, right? To turn on, the depletion layer must vanish by charges injected by the battery. So what is happening? I've explained in diagram as well. So if I just copy this circuit, right? If I just copy this construction, this one. So as soon as I apply a forward voltage which is higher than the I can put it in here, right? Put it in here. As soon as I apply a forward voltage, the charge carriers will be here and they will flow, right? But for this depletion region depletion width to lower, right, we will require some time. Okay, this charge carriers will pass, and as more and more charge carriers pass, this depletion width will lower. But this requires some time, right? And that is basically the forward recovery time. Even though I have applied instantly, it's 100 volts, but charge carriers need to flow, right? More charge carriers need to flow, then only this depletion width will get vanished. So that takes some time, and that is basically the forward recovery time. During the on state, voltage across the diode is low, but for the voltage to reduce, the time required is TFR. Okay, so at that instant only the voltage suddenly won't reduce, right? It will require some time for the voltage to reduce, as we have seen in the switching characteristics. When we turn on a device, the voltage slowly gets reduced and then it goes to very low value, and the current slowly gets increased, then it gets to its steady state, right? So from one steady state to another steady state. This is known as the transient time, and we are studying about the AC parameters, and this is the forward recovery time, the time required for the diode to turn on. Next is the forward, this is more about the forward recovery time. Now under off condition, right, if the diode is off, charges in the drift layer are very few, resulting in very low conductivity and high resistance. So when this is off, right, when this is off, the charges in the drift layer are very low. Okay, in this layer their charges are present are very low, but when current begins to flow, when we apply high voltage, the voltage drop across the diode increases as the drift resistance is very high at T1. So at T1, right, this is the voltage across the diode. What is happening is that it is off, right? Before this is reverse bias, this is off. Now as soon as I increase the make it forward bias, as soon as I increase the voltage of this diode, what will happen? The charges present in the drift layer are very low, hence the depletion width is very wide, hence the drift resistance will be very high. If the drift resistance will be very high, there will be a large voltage drop across the diode. Okay, so the voltage drop across the diode increases as the drift resistance is very high. What will happen? Slowly the charge carriers will start to flow and the depletion width will be lower and the drift resistance will be lower. This is known as conduction modulation that we just studied. So gradually the drift resistance reduces due to conductivity modulation that I have just told you, and hence the voltage across the diode also reduces. The voltage across the diode will reduce as the drift resistance is reducing and the current almost reaches its steady state during T2. So in this time, right, what is happening? The voltage across the diode increased, right? Why did it increase? Because there was more drop across the diode due to the drift resistance. Then the voltage started to reduce again. So this is transient. This we didn't see in the switching characteristics. Okay, this is transient. This is a very short amount of time, but still it will require some time. So here what is happening is that the drift region has very low amount of charges, so the drift resistance is high, hence the voltage drop is also increasing. Current is increasing, hence the voltage drop is also increasing because drift resistance is very high. So after this point, right, what is happening is that there are more charge carriers present in the diode now, in the drift layer now. As there are more charge carriers present, so the depletion width reduces and the drift resistance reduces. Current is still constant, drift resistance reduces due to conduction modulation, or this I can say is conductivity modulation, right? Conductivity. Due to conductivity modulation, the drift resistance reduces, and as it reduces, what will happen is that the drop across the diode will reduce. So it will increase, then it will reduce. So this is due to the drift resistance, and this is due to the conductivity modulation. So in this time, right, the current reaches steady state totally. So this requires some time, and this is known as the forward recovery time. I hope you understood what is forward recovery time. Forward recovery time is basically equals to T1 plus T2, right? This whole thing is the forward recovery time. For it to totally forward bias, right? TFR. This will be TFR. Okay. So like, what is reverse recovery time now? What is reverse recovery time? The process of removing excess charge carriers from the device during turn off so that the device regains its reverse blocking capacity. Its capability is called reverse recovery. So again, if I copy this, right? Copy this. Now what is happening is that now this diode has very low width, depletion width. The drift region has very low depletion width. Now I want to reverse bias. I want to turn this off. So obviously I will make this diode reverse bias. And if I make this diode reverse bias, will this instantly turn off? No, right? There are still abundant number of charge carriers present. So all those charge carriers need to be depleted, need to be taken out, excess charge carriers. So that will require some time those to travel, for these charge carriers to travel and be taken out from this region. So that time is basically known as the reverse recovery time. The process of removing excess charge carriers from the device during turn off so that the device regains its reverse blocking capability is called reverse recovery time. Reverse recovery time, or you can say reverse recovery in general. To stop current flow, a depletion layer must be formed inside the device. Forming the depletion layer again requires obviously some time. We have to deplete the charge carriers. Okay, and the time taken is known as the reverse recovery time. So you can observe here, ID is constant, right? It is forward bias. Now slowly what is happening is that the current is starting to reduce. So as the current started to reduce, electron hole recombination like is happening, right? Electron hole recombination is happening. Negative current flows like in this region, electron hole recombination is happening. So current is reducing. Then after here, right, negative current flows, which removes the excess charge carriers. So we have to flow some negative charge carriers, flow some negative currents to remove this excess charge, so that it can open circuit this diode, right? It can open circuit this diode. We have to flow some negative current as well. Then once the depletion region is formed, once it is free from the excess charge carrier, we can make our current zero again. So like when we reverse bias, right, we apply a huge amount of reverse voltage. We apply reverse voltage, and as soon as I apply reverse voltage, it doesn't instantly go to zero. First it goes to somewhat negative to make this region depleted of excess charges, and as the region is depleted of excess charges, then only the current goes to zero, and then also the voltage also settles. Okay, reverse voltage also settles. So this is happening in the diode. Okay, this is the characteristics, this is happening in the diode. So basically here, right, we remove the excess charge carriers in the diff region. So in the diff region, I told you, right, there are excess charge carriers, those we have to remove. This is done by combined action of recombination and negative diode current. So electron hole recombinations are happening. At the same time, I apply negative diode current so that the excess charges also go away from this diff region. Once excess charges are removed from the diff layer, the depletion layer forms and expands into drift layer. So the depletion layer will form and it will expand, and it will be the drift layer itself, because I have a n minus region over here. After depletion layer forms, the reverse current also reduces to a low value called the reverse saturation current. So it doesn't instantly go to reverse saturation current. It goes to somewhat negative value, then only it goes to reverse saturation current. So here, right, what is our reverse recovery time or time for it to turn off? So it was basically, this was the turn on time. If I say this was the turn on, I can write this as turn on also, right? T on. I told you what is T on in the previous lectures, and this is the T off, right? What is the T off? So in this case, right, T off will be right here. Just hold on. T off will be what? This, where electron hole recombination is happening, then negative current flows. This is T4, for which the maximum negative current flows. Then slowly the current also reduces. So this is also T5, right? And after this only, both of them has reached steady state. So it will be T3 plus T4 plus T5. So don't worry, this is just for understanding purpose. This will not come in examination, but you should know what is happening in the diode and why we have certain turn off time and turn on time. So everything is continuous in nature. So electrons and holes will take some time to travel, and that's why it takes some time to forward bias and reverse bias. It takes some time to turn on and turn off, right? So in this reverse recovery time, there is another term known as reverse recovery charge. So we'll understand about this reverse recovery charge. When a power diode is quickly reverse biased during high forward current, like this is also known as, this phenomenon is also known as hard switching. It needs time to clear charge carriers to block reverse voltages. So this is talking about this thing only. So high current is flowing through the diode, high forward current is flowing, and I am trying to quickly reverse bias it with high reverse bias voltage, negative voltage. So obviously it takes some time, right? It takes some time for the charges to deplete. Exactly that is happening. So from high current, it goes to some peak current, right? Negative peak current to deplete the charges. Then again it goes to zero. We're just linearizing the previous case. Okay. So this time is known as the recovery time, that we have already told, that we have already explained, understood. Now here what is happening is that, just let me give a space here. Just hold on. Yeah. What is happening is that okay, everything will change now. Just hold on. It is TRR, this is QRR. Now the recovery time is a typical metric for evaluating diode reverse recovery. So the recovery time is a metric through which we can like evaluate our reverse recovery, but the better metric is the recovery charge. Okay, reverse recovery charge. Why? Because it takes in the consideration how much maximum negative current we have to flow. That is also we're taking consideration, right? So the current is also, like, huge current is flowing in the negative direction. Maybe we don't want that, so we have to take in consideration the maximum negative current and the time, both of this. And with the area of this graph, I can take in consideration both the time and the maximum reverse current. And what does the area signify? Area signifies the charge, and exactly that is what it is telling us. So amplitude of the reverse current during recovery is a better performance measure than TRR alone. And if I take both the amplitude of the reverse current and the time, it becomes charge, and that is the best measure of diode reverse recovery. Okay, so the reverse recovery charge QRR is the integral of the current, recovery current over recovery time. This predicts the in-circuit performance of the device when it is reverse biased. So if I just compute the area during, like, as it starts to flow, negative current starts to flow and it goes to zero. So like this part, right, this part is IRM by 4. So what we what the actual data sheet or spec sheet tells us is that when it starts to go negative, we start our reverse recovery. When after reaching its maximum negative current, IRM, this is the maximum reverse current, it again goes towards zero. When it reaches IRM by 4, we stop. Okay, we integrate until that area only, but in our case we'll integrate this whole area. That is for ease of calculation, and this is very small area, so it will not provide much error to us, and for easier computation and calculations we will compute only this area. in actual data spreadsheets, they only compute until this, but we don't have to get into that much of level details. Just compute the area of this reverse recovery time, and that's it, right? And we will see they will mention the reverse recovery time, they will mention the graph. I will give you a question and there we will understand this. Okay, so this area is known as the QRR. So yeah, this is the charge. QRR is the charge removed during reverse recovery. This is the amount of charge that has to be removed, right? We had to remove this charge during reverse recovery because there was too many charge in the drift here. So let's like derive a formula. Obviously you can always derive it, okay, but like sometimes people prefer formula, and you can write it in your short notes, just in 1-2 lines, how the derivation happened and the final result. So we are deriving the reverse recovery charge of this particular graph, of this triangular graph. So what will be the reverse recovery charge? So reverse recovery QRR will be the area under this graph, which is IDT, integration of IDT over from 0 to TRR, right? TRR. Now what I observe here is this is a triangle, and like I'm ignoring this fact that I am computing the whole area. Okay, this much part doesn't make much difference, so I will approximate it, right? I will approximate it. So I will approximate it as a triangle, almost a triangle, even though this is a quadrilateral, but I will approximate it as a triangle, So if I approximate it as a triangle, this will be half times base into height. Base is what? Base is TRR into height. Height is what? Height is IRM. Now what is this IRM? Can I compute this IRM? Now if I know the slope of this, right? If I know the slope of this, if I multiply it by T4, I will find out IRM. So what is the slope? The slope is basically delta I by delta T, delta IRM by delta I by delta T, right? Yeah, sorry for the interruption. So this is delta I by delta T. So how can I write it? How else can I write it? So this can be written as di by dt also. As this is a straight line, this can be written as IRM by T4 as well, right? So if I just take this T4 here, so IRM will be equal to di by dt into T4. I will replace it. There is a reason. I will tell you the reason why am I doing this manipulation. So this will be half times di by dt into T4 into TRR. Okay, so this is our formula. Now what is TRR? TRR is basically T4 plus T5. Okay, TRR is basically T4 plus T5. Now if TRR is this, what I will do, I'll just like there is one parameter known as softness factor. For that we have to take in common this T4, right? If I take common this T4, so what will happen? TRR by T4 is also defined as S, which is equals to 1 plus T5 by T4. Okay, sorry, not 1 plus S, sorry, made a mistake over it. This is TRR by T4 is this, and this is equals to 1 plus S. Now what is S? S is equals to T5 by T4. So I will write it here. Like these are just names and notations, so you should know this. For gate point of view, not that important. For ESE and other examinations, right, this can be important. So S is given as simply T5 by T4. Okay, S is given as T5 by T4. Okay, so this is a softness factor, and what I can do is I can replace few things like in terms of softness factor and all those things. So I can write my, like here, right, I can write my T4 equals to what? T4 equals to TRR by 1 plus S. So T4 becomes, in this equation, T4 equals to TRR by 1 plus S, because softness factor is what? Like let's say if this T4 is very high and T5 is very low, so what will happen? It will instantly go to 0 because T4 is very high, right? So it will be somewhat like this, So what is happening? The current is reducing instantly. That's why there is no softness in it. There is no softness. If let's say T5 is more and T4 is less, so it goes here and it has more time to go to 0. So there is more softness to it. Reverse recovery has more softness to it. It takes more time and it has more time to go to 0. Okay, so that's why S is T5 by T4 and it is known as softness factor or snappiness factor. So T4 is this. I can replace this T4 here, right? So everything will be in terms of TRR and di by dt. Di by dt also a important parameter. This I write in small, not in capital. So it is an important parameter for a diode and many power switching devices. Di by dt is an important parameter. We'll understand the significance later on. Don't worry. So this is I by dt, right? I by dt. Okay. So if I replace T4, right, in that equation, so my QRR will become 1 by 2 di by dt into TRR whole square divided by 1 plus S. Okay, 1 plus S. Now QRR is this, right? QRR is this. So if let's say my, like, you can understand the analogy of S here as well. If my S is very lower than 1, so I can ignore this. So this will be almost TRR whole square. So my QRR, right? QRR will be equals to 1 by 2 di by dt TRR whole square, right? So what will happen is that if S is very lower than 1, so obviously T4 is very high. If T4 is very high, it instantly goes to what? Instantly goes to 0. So this is like, this is the triangle only. So this is a triangle. So area is only this only. Okay. TRR is almost equals to T4. TRR is almost equals to T4 and it has no time to get back. Okay. That's why this is like very low softness. Now, if S is normal, right? If S is soft, so our equation will be this only. If S is like in the range or in the order of 1, or I will not write here. If I cannot neglect S, so this will be the same equation, right? QRR will be same. The answer will be same. Okay. So if this is the equation of the QRR, that means my like diode is soft because it is taking more time to like, it has given enough time for me to deplete these charges, right? That's why this T5 has more width now. So I hope you understand the analogy. So S is known as the softness factor or the snappiness factor. Okay, these are just names and not that important gate point of view, but important for other examinations. Okay, so like anyways, in gate you can derive it in seconds, the area of all this, you can integrate and all those things, right? We have studied this in mathematics and all those stuff, so don't worry. So here is an interesting question. During the turning off of a semiconductor device, the voltage and current waveforms are something like this. Okay, voltage and current waveforms are given for a switching frequency of 50 Hz. They have given us the switching frequency. Find the following if the switching period starts from T1. Switching period is starting from T1. Okay, average power loss during switching. What is the average power loss during switching? And reverse recovery charge. Okay, so the switching is happening here only, right? Switching is happening here only. So what is the average power loss? How to compute the average power loss? We know, right? Average power loss is basically the area of the power graph under one time period. Okay, mean of that. So mean of the area. So what is the power of this graph? What is the graph of the power for this thing? So here, right, what you observe is V of t is almost always 0 starting from T1. V of t is almost always 0 at until this junction, right? Until this junction. Only then my power is like power will be non-zero value, because V of t is also non-zero and I of t is also non-zero. Up until here it is 0, so P of t will be 0 because it is the product of voltage and current. So here this is linear, both are linear, so this combination will be something parabolic. This combination will be, product will be something parabolic. So how my graph will look? So my P of t graph, if I draw it, will look something like this. It will start from here, then it will increase at what junction? So here, right, I have t1 time. Here I have t1 time, and this is after 4 microseconds. So 4 microseconds after, what is happening? Both are linear, so this will like the graph will be something like this, parabolic, something like this. Okay, so both are linear. How will it happen? So both are reducing, right? As both are reducing, so this will tend to 0. So like it can be like this as well and like this as well. How can I know if this is like this or this? So both are negative. It is something t squared. If I take the slope of that, the slope will always be positive. In our case, slope will be always positive. If slope is positive, so here, right, the slope is reducing. Okay, but the slope here is negative. No, it is not possible. So slope will be always positive. So this will be something like this. Okay, as in the, okay, in this case also slope is increasing in this case. Okay, the time is increasing. So the slope is negative here, slope is increasing, but here slope is increasing. So if I compute the graph of that, the graph is something t square, and if I find the slope of that, the slope is something linear, right? If the slope is linear and positive, so obviously t is increasing, slope should increase. So here in this case, yeah, slope is increasing. In this case, right, what is happening? Slope is decreasing, right? Yeah, slope should increase. So in this case, it is negative, then it is slightly lesser negative, this is lower negative, and this is the lowest negative. So slope is increasing here, and that will only happen. Slope will increase, not decrease. So in the other case, it was decreasing. So graph will be something like this, and the area under this will be basically my answer, right? And they have given us a time period, right? We know the switching frequency, so from that I can find out the time period as well. So this is 2 microseconds. This is 2 microseconds. Okay, and what is this? What is this peak value? So obviously this graph is not of much use to us, because we will do the mathematical operations only, because obviously finding the area like this is difficult, but just for the understanding purpose. So this is the product of this current and voltage, 300 into 100. So this will be in kilowatts. Okay, I can find this in kilowatts or in megawatts as well, because time is in micro. So if I write it in mega, everything will get simply cancelled. So if I write it in mega, this will be 3 into 10 raised to power 4, and this will be 3 into 10 raised to power like 0.03 megawatts. Okay, why am I doing this? Just to keep the units consistent. So this is my average power and all those things. So now, right, there are two ways to do it. There are two ways how you write the equations. So how do you write the equations? I will write the equations in simple manner. Okay, I will start to write the equations from here. Okay, not from here. What you can do is you can write the equations from here as well. Okay, but I will write the equations from here, and I will just integrate this portion, only this 2 microseconds portion. I will ignore this portion, even though the switching starts from here, but as my voltage is 0, the power dissipated will be 0. So I will write the method 2 in the like after this lecture has been finished. I will write it in the notes, but I will not solve it because that will just waste our time. Okay, both are the same thing, just how you write the voltage and current expressions. So P of t is V of t into I of t. So how can I write my V of t? I will start my V of t from this point, right? Not from this point. Okay, if I start my V of t from this point, what is happening? My slope is reducing, it is going to 0. How much is the slope? It is dv upon dt. It is 100 upon 2 micro. So I will write t in microseconds only, okay, for consistency. So it is minus 100 upon 2 micro because voltage is reducing. Okay, minus 100 upon t, and there is no x intercept. It is 0 because at t equals to okay, at t equals to 2, it should be 0, right? T equals to 2, it should be 0. Okay, there is x intercept here. Sorry, at t equals to 0, it is 0, right? Yeah, sorry, there is a x intercept here. At t equals to 0, it is 0. Sorry for that. This will be plus 50, and same for I of t as well. Same for I of t as well. So it is basically I of t is reducing like this. I of t is reducing like this. Where is it? Yeah, here, right? From here it is reducing from minus 300 amperes. So minus 300 divided by 2 into t. At t equals to 2 micro, it should be 0, right? If at t equals to 2 micro, it should be 0. So it should be somewhat like this. T equals to 0, it should be minus 300. It should be minus 300. Okay. It should be minus 300. Sorry, this will be minus, right? This will not be plus, this will be minus actually. Because at t equals to 0, this is minus 100. Okay, this is minus 100, not 50. Sorry. Yeah, t equals to 2, this is minus 100. Okay, this is not going to 0. Okay, sorry, the slope is positive. It was my mistake. The slope is actually positive. Sorry for that. Slope is positive, right? Slope is not negative, slope is positive. Yeah, that is what I was making the mistake. So this also will be minus, right? T equals to 2, this should be minus 300. Correct. And here, right, t is in microseconds. Okay, so now what will happen? Like the average power, right? P average will be 1 by the switching frequency or the switching time period integration of from 0 to only for which I am interested in, where the power is non-zero, only this, right? So it will be from 2 micro 0 to 2 microseconds into V of t into I of t dt, right? So what is 1 by ts? 1 by ts is basically this 50, right? 1 by ts is 50, so I will write here 50. Okay, there is a 50, so I will write everything in terms of their unit. So V of t and I of t, if I write in mega, so this micro and mega will get cancelled and everything will be fine and dandy. So here what will happen? V of t is how much? This, right? V of t is this 50t 0 to 2 micro 50t minus 100 into 150t minus 300 dt, right? So this will be your equation. So now you have to integrate this. So I will integrate this and then I will come back. So I have done the computation. So like computation is a bit difficult. Why? Because here, right, t is in micro and your frequency they haven't given us in the same units. So just be careful when everything is in micro and this is in volt and kilo, you might mess up in units. So here what is the main crux is, like we have written the equations correctly. T is in micro. So if t is in micro, right, I will not put t 2 into 10 raised to the power minus 6. I will put t equals to 2 only here, right? But what is the important point? Here I have a dt. This dt has a unit of microseconds. This is getting integrated and I am dividing by ts as well. So if this ts has in units of simply s, you will make a mistake because this unit and this unit needs to get cancelled. Only then I will get my watt as unit. So I hope you have studied units very well. So this needs to be also in micro. So what is my ts? Ts is basically 1 by fs, right, which is 1 by 50. This is in normal seconds, but I want to convert this into micro. So I will multiply 10 raised to the power minus 6 on numerator and denominator. So overall this thing becomes what? In micro. This thing becomes micro, right? 10 raised to the power minus 6 is written whatever in whatever expression, if 10 raised to the power minus 6 is written with that will be in micro. So this is in micro and this thing is just stayed away. So I can take this at the top. This will be 10 raised to the power 6 by 50 microseconds. Or in simple words, you can understand. If I want to write this in micro, right, this micro will get converted into 10 raised to the power minus 6. This 10 raised to the power minus 6 will get cancelled and I will be left with 1 by 50 seconds, which I was starting from. So ts is this, right? So I will write 1 by ts. So this will be 50 divided by 10 raised to the power 6. If I take this at the top, this will be 10 raised to the power minus 6. Now I do simple integration and my answer comes out to be 1 watt, right? So you have to be careful with units. Just go through the notes and go through the integration. You will be able to understand. The most important part of this question is basics, right? Just units, nothing else. So P average is 1 watts. We have found it out. So can you tell me what is the maximum power? If someone has mugged up the formula, right, he will say it is VSIS by 4. Vmax Imax by 4. But no, this is not the maximum power this time, right? It is simply these two peaks, right? Because the waveform is different. the waveform is different this time. It is not triangular both, right? It is half triangle and this is full triangle. So you have to understand that as well. So I will write that as well because many students make a mistake. So here they could have asked the maximum power, and maximum power will not be equals to VSIS by 4, right? This will not be equals to this. I will make a good cross sign over here. So my P maximum will be what? P maximum will be this, right? Simply Vs into Is, where these two are maximum. So it is simply Vs into Is. After that, both of them are reducing. So obviously it can be higher than that, as both of the amplitudes are reducing. It is simply 30 kilowatts. If you observe it carefully, it is here, right? I have also written 0.03 milliwatt or 30 kilowatts. Okay. Now, what is the reverse recovery charge? Reverse recovery charge will be the area under this, right? Area under this. So, like the reverse recovery is starting from here. Okay, switching off process is starting from here. Negative current is flowing. So obviously, I will start my TRR. What will be my TRR? My TRR for the second part, right? This is the first part. This is the part 1. The second part. My TRR is basically 6 microseconds, and my IRM is basically 300 amperes, right? 300 amperes. And my what next is there? So my like what is my formula for QRR? QRR is basically the area under the triangle, which is half into IRM. This can come in gate examination, right? IRM into TRR. So it will be simply half into 300 into 6 micro, right? So this time I will write everything in units. So if you want to write in microcoulombs, you can leave it as micro. Okay. Else I will not write it in micro. I will directly write it in terms of coulombs only. So this will be 10 to the power minus 6. So this will be 15 into 6, that is 9 into 10 cube. So this is 10 raised to the power minus 3, or I can write 9 millicoulombs, right? 9 millicoulombs. So this will be the answer. This will be the reverse recovery charge. This will be the answer to this question. Yeah, sorry, like there was one silly mistake here. This should be 900, right? This should be 900. So this should be 10 raised to the power minus 4. Okay, so I can write this as 900 micro as well, or 0.9 millicoulombs as well, whatever you want to write. So you can write this as 900 microcoulombs as well. So this will be your answer. This will be your reverse charge. Okay, so like I am giving you this question homework. In the next lecture, we'll just before starting the next lecture, I will solve this. So this is a very easy question and you can solve this in seconds, right? So I will just quickly classify about more diodes, right? There are multiple diodes, type of diodes. I will just quickly classify about those. So classification of diodes based on reverse recovery time. So general purpose diodes are normal diodes, which we use in signal diodes and which we use in our power diode as well. These diodes are typically made from silicon, which is doped with impurities to create PN junctions. Silicon diodes are widely used due to their good electrical properties, cost effectiveness and stability over a wide range of temperature and currents. So that's why silicon diodes are used, but these are generally slow, right? Due to the impurities present and the silicon and the nature of silicon. Due to this, now what are fast recovery diodes? Which recover very fast. These diodes are designed to switch off very quickly, okay, minimizing the reverse recovery time. This is achieved by doping the silicon with gold or platinum. So here we dope it with other impurities, but we dope this silicon diode with gold and platinum. So if we dope this with gold and platinum, which introduces deep level traps that facilitate higher faster recombination of charge carriers. So this speeds up, okay, our process of recovery. So these are known as fast recovery diodes, where we dope with gold or platinum, which is very rare metal, but we dope with that. Okay, then is Schottky diode. Basically this has no junction, this has basically metal. A Schottky diode is formed by junction of a metal. This is a junction of metal with a semiconductor, typically n-type silicon. Rather than a PN junction, Schottky diode have negligible or no depletion rate. So like this is not at all used in power diodes. Like the main application of power diode is here only. These two are the different types of diode that we should know. For electrical people, we should know all these things theoretically, right? So Schottky diode, basically this doesn't have any depletion rate because this is totally made of a metal. What happens is there is the depletion width is very low, so the time for to recombine the charges, right, is also very low. Okay, so there is no depletion rate, hence it can turn off very fast. So there will be very low reverse recovery time. This will take the maximum, this will take the medium, and this will take the minimum. Okay, so there is the comparison of these two diodes. You can study like approximately the order of reverse recovery for general purpose diode or the power diode is 25 micro, this is 5 micro, and this is in nanoseconds, order of nanoseconds. But do remember that this is the power diode, right? So this is rated for higher values of current. This has a bit lower current than that, and this has the lowest current. Okay, this cannot take very high amount of current, okay, because it is made from metal, and if high current flows, the current density will be higher, and that will burn the device. Okay, that's why this is low depletion region. So the breakdown voltage is also lower, right? The voltage, operating voltages will also be lower. This has higher depletion width, so operating voltages will also be higher. So this is usually used in rectifiers operated around line frequency. Like for low frequency applications, obviously we'll use this in our line and all those things where the power is very high but the frequency is very low. But this is used in inverters and choppers where the power is medium and the frequency is also medium, right? In inverters and choppers we need medium frequency, and this is used in SMPS. So SMPS is also another type of inverter. This we won't study, this is out of scope, but this is mainly used in SMPS where high frequency is there but the power is lowest, right? Okay, so like here there are a few like questions according to whatever we studied, whatever theory we studied about Schottky diodes and other diodes. So you can go through this question, and this question I will solve in the start of the next lecture, and in the next lecture we'll study about the family of transistors. Thank you for watching, and I will see you in the next lecture.